Hello again, dear students. Welcome back to Ferho's website. It's me, Masood. We want to complete our, our solution. We solved 6 questions in previous lesson. We want to complete our, calculation by solving question number 7. Let me read the question for you. Question number 7. A drill starts from rest. You see, it says it starts from rest, means omega I becomes 0. Initial angular speed becomes 0. Omega initial 0. After 3.2 seconds, delta t becomes 3.2 of constant angular acceleration. The drill turns at a rate of 2,628 rad per second. So this value is the is the omega final, right? Omega final, omega f. So what do we look for? A, it has 2 parts actually. Part A says find the drill's angular acceleration. We look for alpha. Is information available for finding alpha? Yes. Alpha is equal to omega f minus omega I divided by delta t. This is the rearranging of one of the kinematic equations, right? This is the equation. Omega f becomes omega I plus alpha delta t. Whenever you rearrange it for alpha, you get this form, which is familiar for you, I'm sure. Alpha is equal to omega f, this number, minus omega I becomes 0, divided by 3.2. And the answer will be 821.25 rad per second square, right? That's it. B, part B for the same question. Determine the angle through which the drill rotates during this period. So what do we look for? We look for delta theta. For the same information, we look for delta theta. Omega I, 0. Delta t, 3.2. Omega f, the same information, but here we look for delta theta. How do we look for delta theta? How do we find delta theta? By using one of the kinematic equations in angular, angular motion. This equation works. It's very easy. Delta theta is equal to 1 over 2 bracket omega I plus omega f multiplied by delta t. Substitute the value, omega I becomes 0, omega f becomes this number, multiplied by 3.2. Teacher, how do you calculate this, this algebraic, term? So I want you to, calculate the value within the bracket. After that, multiply by 3.2, divided by 2. So you get the 4,205 rad approximately. That's it. Let's move on to question number 8. Question number 8, it says, when a wheel rotates about a fixed axis. A wheel, imagine there's a wheel, rotates about a fixed axis. Do all the points, right? Do all the points on the wheel have the same tangential speed? Does it make sense to you? Does, tangential information, or do tangential informations remain constant? It doesn't make sense, right? Because, tangential information, like tangential speed, tangential acceleration, depend on the radius of the circular track. The farther the, point is from the center of rotation, from the axis of rotation, the larger the tangential speed is, the larger the tangential acceleration is. That's why the answer is no. It says when a wheel rotates about a fixed axis, do all the points and they will have the same tangential speed? No. They have the same angular speed. This is the answer of teacher's book. Number 9, correct the following statement. We have a statement here. We have a statement here. What's the statement? Let me read it for you. It says the racing car rounds the turn at a constant velocity of 145 kilometers per hour. So what's wrong with this sentence? What's the problem of this sentence, right? If you take a look at the information, it says the racing car rounds the turn at a constant, right? Does constant come with velocity? In physics, constant does not come with velocity. Constant should come with speed, not velocity, because velocity is a vector quantity, it's not scalar quantity, and let's say velocity never be constant because it's a vector quantity. But if you change the velocity, this term, this word actually, if you turn this word to the speed, it's right, it's true, right? It will be true. So the racing car rounds the turn at a constant speed of 145 kilometers per hour. That's it. Let's move on to question number 10. Describe the path. Describe the path of a moving body, right? Describe the path of a moving body whose acceleration is constant. No problem, acceleration is constant means the object rotates at constant rate with the same rate, right? In magnitude at all times and is perpendicular to the velocity. So it focuses on what? It focuses on acceleration, right? It says describe a path. Think about a path whose acceleration is constant, right? And acceleration is perpendicular to the velocity. So in which situation, look here, in which situation acceleration is perpendicular to velocity? Only in circular track. Only in circular track acceleration is perpendicular to velocity only. For example, teacher, what do you mean by this? How do you know that? Let me examine it for you. For example, there's a straight line path like this, right? A car moves, let's say, forward. This is, let's say, velocity, right? And maybe the car speeds up or slows down, no problem, right? The car changes its velocity, whether, let's say, it decreases or increases, no problem. So in this situation, there is acceleration as well. For example, we have speeding up, no problem, or slowing down. If you have a slowing down, acceleration becomes opposite in direction, no problem. So which type of relationship is there between velocity and acceleration in a straight line path? V and A are parallel. So the path shouldn't be a straight line for this condition. Acceleration is perpendicular to velocity only in circular track. Teacher, could you give us example? Could you draw it for us? Yes. There's a circular track. The object moves, let's say, around the circle, right? It has tangential velocity and tangential acceleration, let's say, to the tangential acceleration toward the center of a circular track, and tangential velocity or tangential speed to the tangent of the circular track. So in this situation, you see, they cut one another. They make a right angle. That's why they are perpendicular. So the path should be circle. For achieve this, let's say, condition. For achieve this condition, let's say the path should be circular track, not a straight line. Let's move on to another question, which is question 11. Question number 11, it says, an object moves in a circular path with constant speed. Constant speed. There's no, let's say, it's a circular track. There's no tangential speed. Tangential speed is equal to 0. Is A, so it has two parts. Is the object's velocity constant? Explain. No, velocity is not constant. I told you, because it says velocity. Velocity should not be constant because velocity, let's say, consists of two parts. It has magnitude and it has direction. If magnitude velocity constant, no problem, it's okay. The object moves with constant, let's say, speed. But here, let's say, is the object velocity constant? No. So velocity, I told you constant velocity does not come with one another. Constant speed, it can be, but constant velocity, it doesn't make sense in physics. That's why we say no, object's direction changes. Because object's direction changes, velocity can't be constant. B, is its object acceleration constant? Is acceleration constant for the object moving around the circular track or not? Explain. No, acceleration is not constant. Maybe AC changes its direction. That's why, let's say, centripetal acceleration, you cannot, it can be constant. Centripetal acceleration changes its direction. So is its object acceleration constant? No, it's not constant. AT becomes zero. Why do we say, teacher, why do we say AT become constant? How do we know this? Take it from the text, right? It says constant speed. Constant speed means the speed does not change. So AT becomes zero. And AC, why do we say AC is not constant? Because AC changes its direction, let's say, whenever it circles the square, right? Here, or circles the circular track. Here, AC downward. Here, AC points to the left. Here, AC points upward, and so on. So AC, centripetal acceleration, can't be constant, and AT is equal to zero. So acceleration, object's acceleration can't be constant. Number 12, give an example of a situation in which an automobile driver can have a centripetal acceleration, right? But no tangential acceleration. Think about the situation, think about the case. An object has a centripetal acceleration. So automatically, without thinking, unconsciously, you can say, teacher, the object or the car, a car moves in a circular track. It's true. Automatically, the path gives the object centripetal acceleration, but no tangential acceleration. Think about the situation in which AT is equal to zero. In which situation AT is equal to zero? When the object velocity, when the object speed is constant. So you can say, this is the answer, a car driving a circle at a constant speed. Whenever you say driving in a circle means you mention centripetal acceleration, because circular track provides the centripetal acceleration automatically. But why do we say constant speed? Because it says no tangential acceleration. Constant speed, especially tangential speed. Number 13, can a car, look here, can a car move around the circular track, racetrack, so that the car has a tangential acceleration but no centripetal acceleration? Is it possible in your opinion? I'm sure you know the answer because you understood the subject. And I told you, in any circular track, any circular track, let's say, provides a centripetal acceleration, let's say, directly, automatically, and you cannot, let's say, you cannot have zero centripetal acceleration. You cannot eliminate centripetal acceleration. Centripetal acceleration is a necessary, actually, for circular track. But about the first part of the question, it can be, it says that the car has a tangential acceleration. No problem. Car, in which situation car has a tangential acceleration? When the car speeds up during a circular track. When the car slows down during a circular track, no problem. But about the second one, it can't be. It's impossible. So let's say I told you in previous lessons, and I emphasize on this. I emphasize on this information. I told you that the circular track, and I can say, in other words, centripetal acceleration never be zero. It never becomes zero. This is the answer. No, AC is necessary for circular motion. AC is necessary. Question number 14. Let me read this question. The gas pedal and the brakes, right? We have two pedals, gas pedal and brakes pedal actually, of a car are used to change the velocity by accelerating the car or decelerating it. Could a steering wheel perform either of these actions or not? Let's explain it. What's the answer? Can I say a steering wheel can be an alternative for brake pedal and for, let's say, gas pedal as well? Yes. Yes, steering wheel changes velocity by changing the direction of motion. Because a steering wheel changes the direction. This is a steering wheel, right? The driver, whenever the driver changes the steering wheel, so it changes the direction. Whenever it changes the direction means it changes the acceleration. It changes the velocity. Let me give you an example about this case, right? Teacher, how does a steering wheel, let's say, be an alternative for example, gas pedal? How does a steering wheel, let's say, speed up the car? Let me give you an example. For example, you stop the car, right? You stop the car, and the car, if you let's say stop the car for example, in your yard, yeah, in your house yard. In this case, how do you, for example, let's say, speed it up by means of a steering wheel? Just by turning the steering wheel, the car starts its motion. The car, let's say, speeds up. It starts from rest, let's say, and it picks up a velocity. That's why a steering wheel can, let's say, can speed up the car just by turning the wheel, right? Just by turning. Actually, if the car is in neutral case, and the handbrake actually, you put down the let's say handle brake, actually in this situation you can, let's say, speed up the car just by turning the steering wheel. Teacher, how does let's say steering wheel be alternative for the case of slowing down? How does a steering wheel slow down the car? Think about the situation. God forbid the car, for example, does not have brake. The brakes stop from working, right? The brakes does not work in this situation, and the object, let's say the car, let's say gradually speeds up, right? In this situation, how does the driver, let's say, what does the driver think about? The driver thinks about what? Thinks about turning the steering wheel. Whenever the person turns the steering wheel, in this situation, the car gradually slows down. That's why a steering wheel is an alternative for the speeding up and for the slowing down. And I can say a steering wheel is an alternative for gas pedal and brake pedal as well. That's it. Question number 15. It's a problem. I'm gonna, before I let's say solve this problem, I'm gonna let's say leave it for the next lesson. I appreciate you guys for watching this video, and bye for now.